cosmological constant, said it was his biggest blunder, he wanted to throw it away. But it turns out it's kind of like trying to put the toothpaste back in the tube after you've gotten it out. If Einstein hadn't introduced this term, someone else would have, much later. Because nowadays, we think of it in a very different way. And due to the miracle of modern mathematics, we can rewrite this equation. This is a small step for a mathematician, but a giant leap for a physicist. Not that it's that hard to take this term and put it over there, that's not so hard. But in physics, equations mean something, unlike mathematics. And in physics, the left-hand side involves curvature, and the right-hand side is energy. And this term, when you bring it over here, looks like a new contribution to the energy and momentum of the universe. What could give such a contribution? Only one thing. Nothing. By nothing, I mean nothing. I mean, if you take a region of space and get rid of all of the particles and the radiation and the cameramen and everything, and it's completely empty, if it still weighs something, then it will give this kind of energy, this kind of term. Now that's crazy. Empty space can't weigh anything. Okay? I mean, if you ask a 4-year-old, I was going to say a Republican candidate, but let me ask a 4-year-old, what's the energy of empty space? They say nothing. And that's right, but the 4-year-old hasn't taken quantum mechanics and special relativity. Okay? You put those two things together, and it turns out empty space ain't so empty anymore. It turns out empty space is a boiling, bubbling brew of virtual particles that pop in and out of existence at a time scale so short you can't measure them. Now, that sounds like trying to count angels on the head of a pin. If you can't measure them, it's philosophy. But in fact, we can't measure the virtual particles directly, but we can measure them indirectly. Here is the actual animation of a real calculation in physics of what the space inside of a proton looks like. It was shown at the Nobel ceremonies a few years ago, and I got it when I was there. Because the theory that allowed us to calculate this won the Nobel Prize that year. And the amazing thing is that we not only know that there are these virtual particles and fields popping out of empty space, but when they have an effect. You may have learned in school that protons are made of particles called quarks, and protons have 3 quarks in them. But it turns out if you add up the mass of all the quarks, they only add up to 10% of the mass of the proton. Most of the mass of the proton comes from these virtual particles that are popping in and out of existence. And since you're made of protons and neutrons, most of your mass comes from those virtual particles. And you wouldn't be here, therefore, if they didn't exist. So we know they exist. That's just one of many reasons that we know they exist. We can do calculations that predict accurately how the universe behaves, but only if you have these weird particles popping in and out of empty space. Well, good. Now, if you can calculate the energy inside of a proton, what about the energy of truly empty space due to these virtual particles? Well, we do the calculation, and we go from one of the most remarkable and best calculations in all of physics to the worst calculation in all of physics. Because when you do it, you predict that the energy of empty space should be roughly a gazillion times the energy of everything we see. And that's impossible. If that were the case, the universe would be expanding so fast we wouldn't be here. And indeed, this problem has been around since I was a student. It's called the Cosmological constant problem. And it was the worst problem in all of physics, which is why we never talked about it. But we knew the answer. See, we're theorists. We knew the answer. The answer's got to be 0. It's the only sensible answer. I mean, it has to be 0 because you can't imagine canceling that big number to 120 decimal places and leaving something non-zero in the 121st decimal place. But you can get 0 very beautifully in physics. Mathematical symmetries allow things to cancel equal and exactly, producing 0. So we knew that there was another symmetry in nature that we had discovered, and the number was 0, and we could go to sleep. But the universe is the way it is whether we like it or not, as I tried to tell you before. And that means we actually have to go and find out. Just because it seems sensible to us doesn't mean it's right. In fact, what's sensible to us is just usually something that's very myopic. So, let's measure the energy of empty space. Well, how would we measure it? Remember, if we put energy in empty space, it produces a term that's like Einstein's cosmological term, and that is gravitationally repulsive. So we measure the Hubble plot, which when Mr. Hubble measured down here. We should measure if the energy of empty space is really non-zero, the universe should be speeding up. A sensible universe should be slowing down. And in 1998, two groups of astronomers, who also didn't know what the hell they were doing, were measuring the rate at which the universe was slowing down. They knew that what they were doing. They wanted to measure the rate of deceleration of the universe. And they published in Science magazine, again, the following picture. And this is an amazing picture. It may not seem that way, but it was the cover of Science magazine, actually. Here's the Hubble plot. Now, in order to make it clear, I'm just going to draw a straight line through this data set, bring the whole thing down here. And if the universe is decelerating, as a sensible universe should do, all of these distant supernovae they've measured should fall along that curve. But of course they don't. They don't even fall below the straight line. So what could that mean? Only one of two things. The data's wrong, which it usually is, or the universe is speeding up. The expansion of the universe is speeding up. Now, just for fun, if you want to ask how much energy would you have to add to empty space to fit that data, here's that curve, it turns out what you have to add is exactly what we were missing. If you add 70% of the energy of a flat universe and put it in empty space, everything works out. And that's the picture of the current universe. It's a cockamamie universe in which 70% of the energy resides in nothing, 30% resides in some other kind of material that's not made of the same stuff as we are, and we are a little bit of cosmic pollution that's left over. So much for a universe that's made for us. So it's the first lesson I want to give you, is that you are much, much more insignificant than you thought. And in fact, nothing is really very important. It's what motivated me to write the book. Because not only is the dominant energy in the universe resides in empty space, but the most exciting thing about it, from my point of view, is we have no idea why it's there. That's incredibly exciting. It means there's a lot left to do. And if anyone comes to you and lectures to you and tells you they know why it's there, they're lying. Especially if they're a string theorist. Its existence is probably tied to the beginning of the universe, which makes it interesting. And it will determine our future, as I'll talk about. It's changed everything. Now, speaking of our future, remember I got into the business because I wanted to know how the universe would end. And it turns out there's a simple way to do it. If I had a coin, which I don't think I have, I do. Big enough for me to catch, too. So I have a coin, if I throw it up, it comes back down. If I throw it up higher, it takes longer to come back down. If I throw it up really high, it doesn't come back down. Well, if there's no ceiling, it doesn't come back down at all. It escapes the Earth. And now, we teach high school students how to calculate that. Kindergarten students nowadays, probably. And you all remember, and fondly remember, this equation. Doesn't matter if you remember it. It turns out there's a simple way to determine if that coin will come back down. We know from Newton, well, past Newton, but we now know that there are two types of energy. When I throw a coin up, I give it a positive energy, called its kinetic energy, which is related to its motion, and there's a negative piece, which comes from the gravitational potential energy, because the Earth is pulling it. And it turns out we turn the whole problem into a bookkeeping problem. If we add up these two pieces and the total energy is bigger than zero, the object will escape. And if it's less than zero, the object will return. That's simple. So we keep in order to make that piece bigger than this one, we got to pump up the velocity to 11 kilometers per second from the Earth, for example, to make it escape. Great. Well, it turns out we can do the same thing for the whole universe. Because if the universe is the same everywhere, then anything that happens in one place will happen everywhere. So just consider a small region of the universe with us at the center. And now we have a galaxy at the edge of that region, and Hubble tells us it's moving away from us. And if that galaxy has positive energy, it'll continue to move away from us forever. Now, how can we determine its total energy? Well, just like I told you, there's a positive piece coming from its velocity, which Mr. Hubble told us. And there's a negative piece coming from the gravitational attraction of all the galaxies and dark matter in that region inside of it, which we've now measured. And if this negative piece is bigger than the positive piece, B over A is bigger than 1, the energy is negative, that galaxy will stop and return. And if it stops and returns, the whole universe will do that. The universe will collapse. If B over A is less than 1, it will expand forever. But what is amazing is that B over A is nothing other than this quantity omega. It's the curvature of the universe. And if B over A is exactly equal to 1, which is what we measured, What does that tell us? That tells us the negative piece is exactly equal to the positive piece. What does that tell us? It tells us the total gravitational energy of the universe is 0. Now, if you were going to make a universe from nothing, what would you give it? The total gravitational, it didn't have to work out that way, but the total gravitational energy of every object in the universe is 0. Is it only such a universe that could come from nothing? And now I want to spend the last few minutes talking about universes from nothing. The first kind of universe, the first kind of nothing, because I have to redefine nothing constantly to try to appease philosophers and theologians. Well, I really don't like to appease them, but just to be logical. The first kind of nothing is the kind of nothing that was written about in the Bible, I would say, and classical philosophy. An eternal, empty, dark void. That's a pretty good definition of nothing. It used to be. Well, it turns out that kind of nothing will always make the universe, because that kind of nothing is unstable. The laws of quantum mechanics tell us that if we take eternal, dark, empty space, quantum fluctuations will pop particles in and out of existence in time scale so short they can't measure them. Well, that doesn't have something in it because there's no particles. But when we add gravity to the mix, gravity can have negative energy. And if I pop two particles out of empty space that have positive energy, but the gravitational attraction is so big that the negative energy equals the positive energy, I can take those particles and pop them out of nothing with impunity. They don't ever have to return into empty space. And so therefore, you are guaranteed, if you wait long enough, if you have empty space, it will start filling up with matter. Empty space is unstable. Nothing in that definition is unstable. It will always create something. So what's the big deal? Well, I say that, and then people who a few years ago would have been happy to have an eternal dark void be nothing, say that can't be nothing because you can create something from it. So that's not good enough because you don't have particles, you don't have stuff, but you got space. Well, where did the space come from? Well, that's what I just said. Well, the thing is, when you add gravity to quantum mechanics, when you put gravity in the mix and we consider a quantum theory of gravity, then it turns out that means we make space a quantum object. Then space itself can pop in and out of existence from nothing. And in quantum gravity, I can create universes I can create whole spaces where there were no spaces before. And on small scales, baby universes are popping in and out of existence on a time scale so short we can't measure them. But that's not a universe. You can tell from this lecture we've been around for more than just a brief instant. It seems like an eternity. But if I could create a universe with 0 total energy, then it could survive with impunity. So you might think it's all simple. Well, we create a flat universe, but it's not that simple. I wish I could say it was, because that'd be easier, but I want to tell you the truth. It turns out we don't know how to calculate the total energy of a flat universe, because I just talked about the gravitational energy, but there are other components of the energy. There's the rest mass of objects. And it turns out one thing we do know for certain, however, is that that closed universe has 0 total energy. So closed universes can pop in and out of empty space with impunity. But we don't live in a closed universe. Well, okay, but here's the problem. Closed universes that pop in and out of empty space, closed universes will expand, stop, and contract again. And most closed universes, if quantum gravity is important, are extremely small. And they will collapse on a time scale of 10 to the minus 43 seconds. A very short time. But how do you make a universe last for a long time? Well, if you pop a closed universe out of empty space, but before it could collapse, you put energy in empty space, then that universe will start to expand and expand faster and faster and faster and blow up. And in fact, given our theories of particle physics, we, in fact, are very confident that that's precisely what happened in the early universe. Because if you allow empty space to have energy, not only will it make the universe blow up very fast, but quantum fluctuations will produce lumps that will be left over, lumps that you can measure in the microwave background, and the lumps we see in the microwave background have exactly the character of quantum fluctuations in that kind of space. So we have great confidence that that happened. But you see, If you pump up a flat and closed universe, it's like blowing up a balloon. As a closed universe becomes larger and larger and larger, it'll look flatter and flatter and flatter. So the only closed universe you could create from nothing that would last long enough for me to ask the question is one that looks flat. And therefore, if you had a universe created from nothing, its characteristic would be that it would look flat. And that's precisely the universe we live in today. Again, it didn't have to be that way. Now, does this prove the universe came from nothing? No. It's just consistent with that possibility. And every measurement we make of the universe is not only consistent, but suggestive of that possibility. And I find that absolutely remarkable. And worth celebrating, as I'll talk about. Now, okay, that's what I just said. However, when I say that, people will point out to me, especially theologians, that's not absolutely nothing, because you can create something from it. You may not have particles, and you may not have space, but you have the laws of physics. Who created the laws? Surely you need God for that. Well, let's kill God. This is a brief history of time. It's the last graph you'll be happy I'm going to show you. This is the density of matter as the universe expands. It goes down. And this is the energy density of empty space. And this is a picture of the history of the universe, and this is now. 13 billion years after the Big Bang or so, when the energy of empty space is about 3 times the energy of matter. Now, when you look at this picture, you see something that's very frustrating, very worrisome. And that is, we live in the only time in the history of the universe when those two numbers are about the same. At all earlier times, the energy of empty space was much bigger than the energy of matter was much bigger than the energy of empty space. At all later times, the energy of empty space is much bigger than the energy of matter. We live in a very special time, but we're not supposed to live in a very special time. Copernicus told us that. Why 13.7 billion years after the Big Bang should we be in such a special time? Well, it turns out people have argued this is the reason. Galaxies exist. And why would that be the reason? Well, let's go back to this picture and say, let's say the energy of empty space were 50 times bigger. Well, then you'd have this line instead of this one. These two curves would cross at a different time. What time would that be? Well, that would be the time when galaxies first formed. But the energy of empty space is gravitationally repulsive. If it dominated the expansion of the universe before galaxies formed, then galaxies wouldn't form. Before the matter could collapse, it would be pushed apart. And if galaxies couldn't form, then stars couldn't form. And if stars couldn't form, then planets couldn't form. And if planets couldn't form, then astronomers couldn't form. So there's this, maybe this is telling us something, and it's led to something I call anthropic mania, which is just what I said. And this would mean, this one, if there are many different universes and each one has a different energy of empty space, then only those in which it's not much greater than what we measure will galaxies form, planets, stars, and astronomers. So the universe is the way it is because there are astronomers here to measure it. Now, it sounds ridiculous, but it might be true. It sounds almost religious. It sounds like the universe was created, so we would be here, right? That's not right. It's more like evolution.